Hello and welcome to HSD Tutorial-9 on Post Layout via FEM simulation in ADS. In this tutorial video, we shall focus on key steps involved to perform full 3D FEM simulations on high-speed via. It is recommended that you watch earlier video on how to import a board file into ADS. So here, for this example, we will be using a Xilinx KC105 board which has all kind of interfaces. Now first let's look at the stackup we have. It's a 16 layer stackup which we obtained by importing the BRD file into ADS, or you can also import ODB++ file if you have. The three windows which are quite useful is Navigator, Layers and Properties window. In case you don't see it, you could always activate it by going to Command View, Docking Windows, and then selecting one by one of these three windows. Now once these basic windows are in place, we can easily navigate through the desired nets by going to Navigator window and typing the name. So in this case, we are interested in doing a few analysis on a PCI Express, one of the differential nets. By selecting those, we can see the nets get highlighted. We could either take the entire net for our simulation or just the VIA section. In this tutorial, we will focus more on simulating the VIA transition on this differential pair. So first of all, let's go ahead and save as our design so that we don't end up disturbing the original imported design. So I'll give it a new name, and then once the new layout is created, for this board file, we will go ahead and proceed towards filtering out the desired section on which we would like to run analysis. Now in the last step, we have already identified the area which we would like to analyze it using FEM. Now the job is to do a cookie cutting so that we only have the portion which we really want to simulate. This can be easily done by making either a rectangle or a polygon as an outline to the area which we want to cut out. Now while selecting the area, it is important to remember so not to disturb the return path. Otherwise the simulation may not be accurate. So here, as you can see, I marked a rectangle with sufficient space around the section which we want to simulate. Now we can select the rectangle and use one of the icons of crop to selected, or else if this toolbar is not visible, we can right click anywhere and activate edit shapes. Otherwise we can also go to edit, modify and crop to selected command. By clicking on crop to selected icon, it will chop off all the necessary piece from our board layout file and only leave the area which we highlighted by using the rectangle. Now you can also observe there are a few hatch patterns. Well, they represent net overlap based on the net connectivity engine. We can switch it off using the menu as shown here in this video to not to show net overlap zone. So now once we have the geometry for our simulation, we can click on any of the trays and we can see the desired details in the properties window. So here we can see the two traces which are connected by VIA is on SIG5 and top layer. By going to layer tabs, we could switch on and switch off any of the layers which we don't want to see. However, before we do that, let's go to stack up and observe where are the traces. So one is on the top layer and GND1 is the ground layer, and this is a typical microstrip configuration. The SIG5 is towards the bottom side, and we can see it's kind of strip line, but not a classical strip line, a little offset strip line. And out of two ground planes, GND7 is the closer ground plane to our SIG5 trace layer. And this information is what we need right now. Now we can go ahead and switch off all the layers and just inspect the area for the transition which we want to analyze. So we will only switch on edge top, SIG5, and then the drill layer, which is drill top bottom as per the naming convention used in the board file. One of the cool features in ADS 2017 onwards is to press 3 to render the layout into 3D. Now this makes it very easy to inspect the area, the transition which we would like to simulate. We can not only see the geometry in 3D, but we can also perform all kind of editing operations while in 3D mode. So let's go ahead and activate three ground layers which we have for our VIA transition, which is GND1, GND6 and GND7. So this is a typical transition which we are looking at to simulate, and this 3D view makes it quite intuitive for us to see the structure which will be eventually simulated. Now another part also which we can do is to activate edge bottom and look at the via caps which we will have on this layer. Now if needed, we can go ahead and switch on other layers as required. But for FEM simulation, remember it's a full 3D electromagnetic tool. So we would like to remove whatever unwanted metals we can while maintaining the performance of our structure. So I'll go ahead and switch on all the signal layers, and we can see there's nothing much on those signal layers, and these scattered pieces do not affect our simulation accuracy. So I'll go ahead and delete them. And then once activating all the layers, these are the structure, or these are the layers which eventually will get simulated. And we see a few floating items on bottom layer. We'll go ahead and delete those scattered items as well. So this is pretty much what we would like to simulate for the via transition in this design. So we can press 2 on the keyboard to come back to the 2D entry mode, and now we will go ahead and place the ports, or the pins as we call it. Now one of the nice things which you could do to improve accuracy of FEM simulation is to measure the trace width on either side, because eventually we would like to apply an edge port, and we would restrict the ports to only align with the dimension of the trace where we are going to apply. So in this case is 5.5 mil and 4.75 mil in any of these traces. Now click on edge top layer, makes it a current entry layer by clicking on the pin icon. By default you will get a port shaped dot, but we will go ahead and switch on edge and then enter the dimension which we have measured for the particular trace. By selecting the length, now we can see there is a horizontal line along with the port, and we can click on the port or the location where we want to place the pin. You can see the blue line which is representing the edge size of that pin which we have placed. Now on the other side, if things get difficult to see, you can switch on and switch off any of those layers. We will click on a SIG5 and go ahead and place 2 pins on the trace which is created on SIG5 layer. By clicking on those, you can notice very clearly the edge. Now if needed, you could restrict the edge size to be 4.75, but that's okay to have a little more than what is the trace size. Now we will place the ground pins. So we click on GND1 layer and place 2 pins on GND1 for P1 and P2. And similarly, we will click on GND7. So if you recall, GND7 is the closer ground plane for our SIG5. So we'll go ahead and place 2 negative pins on GND7. So clicking on that, make it active layer for entry. We'll rotate the pin and place 2 pins on GND7. So now we have all 4 pins which is required for a differential transition. We will go ahead and make a proper plus and minus pairing of these pins to create ports. Clicking on the port editor icon shows us all the default definition of the pins which we have. So we will go ahead and unselect auto center and hide the connected pins which are already connected. We don't want to see them. We can collapse, and we can notice, because of our placement, port number 1 and 4 are our signal pins, 5 to 8 are ground pins. So we can right click and remove, and now we can expand our definitions of the pins which we already have, and simply drag and drop respective pin to the GND pin of a particular port. Now if you have followed a particular sequence while placing these pins, this job makes it very, very easy. A simple drag and drop. So now we have proper plus and minus pair, and we can go ahead and verify by clicking on the individual ports and make sure the right combination has been created. If not done properly, this will give us an inaccurate response in FEM. So we can go ahead and save our design, and now we can set up our EM simulation for the FEM run which we want to do for this via transition. Pick any of the templates. I typically choose RF board, and then we can go ahead and modify. So the first thing to do is to select the right solver. In our case, we want to use a full 3D FEM instead of using momentum. Click on substrate icon and make sure we have the right substrate, which in this case is. The port assignment has already been done and there is no problem with the port assignment. So we will simulate this via transition from 100 megahertz to 15 gigahertz. So we'll go ahead and modify the default frequency sweep plan and have maximum number of points as 101 in this range. Another very important thing to set up accurate FEM simulation is to set the options properly. So first thing which we have to set is lateral extension, which is substrate size in XY direction. Now because we have taken care while cookie cutting, we can only have a small portion like 0.1 mm. And vertical extension is basically FEM padding, which is air on top and bottom side. The boundary condition could be open, which is absorbing boundary condition for our VR transition. Going to mesh tab, we can define the meshing stop criteria. So we are okay with delta error of 2%, that is 0.02, and rest of the options we can leave as default. Under refinement, we can define the meshing frequency, which in our case would be maximum frequency, that is 15 gigahertz. Now we could set some advanced options for meshing, like target mesh growth from one iteration to another iteration and so on, but we'll leave it all default. In the initial mesh, one of the things which we can use to improve FEM accuracy is to have a conductor mesh, but we do not want to have edge meshing for all the conductors we have in design. So we will go to layer specific tab and only define the edge meshing on edge top and sig5. A typical thumb rule to be used is 1/3 of the width of the trace. So in this case, approximately that turns out to be 1.5 mil. So I will go ahead and activate edge meshing on sig5 and edge top of 1.5 mil. Rest everything can be left default. Under solver, there are two order basis function, first and second order. One is for electrically small structure, another one is full structure. So we'll go ahead and use mixed order and leave it to ADS to decide which order of basis functions to be used. Click on simulate button to start FEM simulation, and the simulation time will depend upon how many number of cores or threads you have, what is the CPU speed. In my case, it takes approximately 38 minutes to finish the FEM simulation on this structure, which is quite reasonable, and it takes about 2 GB of RAM to simulate, which is quite decent. Now, more number of frequency points will result in longer simulation time, again depending upon your PC power. So here are the results for our VR structure, and we can notice the decent performance in transmission, return loss and so on. But note these are single-ended S parameter results. To check mixed mode response, we can simply use S parameter checker available in the schematic page. So we will enable the HSD toolbar in schematic by right clicking and then click on check view S parameter window. And here we could either use a touchstone file or a dataset file. So in our case, we have dataset. By changing mode to dataset, we can select the right dataset for analysis, which is our FEM simulation. And now we can observe the entire characteristics of our VR results. We could click on the single-ended components to display all the S matrix. We can check whether our results were passive or not. By going to mix mode, we can click on the right port numbers and right click and make them as a differential pair, and then calculate mix mode data. We have the entire mix mode characteristics. By clicking on SD1, D2 means differential transmission, we can observe the magnitude and phase response. And also by clicking SD1, D1, which is the differential return loss, and also we can look at the mode conversion, from common mode to differential, differential to common mode, and so on. So this utility makes it very, very easy to to diagnose the results which we have obtained from performing FEM simulation. Right, so one last thing, so once we are satisfied, we can close this window, and the VR performance seems to be pretty nice, and differential responses is what we expect. To gain more insight into FEM simulation, we can click on visualization window. So this is more like a 3D field plotting window where we could see the E field, H fields, and how the meshing has happened during FEM simulation. So we can notice we have air and the various dielectrics. So we can enable or disable any of those layers to be highlighted or keep it in outline mode. And we can also switch on the mesh in either the air or any of the other dielectrics. By activating the mesh in air, we can see all the tetrahedrons which were created for FEM simulation for our structure. We could also activate the meshing in various dielectrics and see how various pieces got meshed. By switching on the surface mesh and clicking on volume mesh, we can see more like a 3D filled meshing. And now you can notice how the different areas got meshed for our FEM simulation, and you can notice the adaptive nature of the tetrahedrons which we have. Hope you enjoyed watching this tutorial video. Subscribe to my YouTube channel for more such videos, and hope it will help in your design work using FEM simulation in ADS. Thank you very much for watching the video.